All right, I'm gonna go ahead and start with these problems here. All right, continuing with what we kind of discussed last time, right? We're talking about the average rate of change, right? And what we want to do is kind of focus on the behavior we see with functions that we deal with, right? Increasing, decreasing, constant. Those are some things that you kind of, as I mentioned from college algebra, we talked about. We want to build upon that, okay? Now we're going to add some things to this as we go today, but I wanted to start here by just going through the operations of the average rate of change. So let's look at that process. So to make sure we have it, do we agree then the f of 2 is going to be equal to 3? So I plugged in 2 into the function. Okay. Now I use synthetic division. If you remember, synthetic division is a great way to get through there quickly. That's where I got my 3 from.
Just do it normally, like
you could do it normally. I'm just saying, like I said, I did synthetic division in my head. That's all. Okay. But the whole key is we're plugging it into our function. We actually need to do that with all of these points though, right? So as I go through there, that is definitely a starting place. So make sure that like, hey, I know this is 3 now. If we plug in 5 though. So I got, what we get for 4. And then 3. We all in agreement there?
I guess my question is on the test is about which way.
It does not matter.
Any form.
Any form. You could have plugged in a calculator for all I know, right? Right. So you had negative 25 plus 10 plus 3, right? We have to watch our signs there because it's a plus 10 and a plus 3. I can see where you got 38 from though, right? It should be minus 10, huh? No. You're right. I negative 25 minus 10 plus 3. Sorry, you are correct. I messed up. So did you say 32? No, we plugged in a positive 5, right? I'm second guessing myself now. All right. Yeah, so
we were both a little confused because I was thinking that whenever you plug in the 5 into the square, you put parentheses around the 5.
yeah, that's negative 1 times 5 squared.
Yeah, not negative.
You order of operations, you do exponents first and then you deal with multiplication. So you have to be careful. Yeah. Okay. Better? Gotcha. Gotcha. Now, keep in mind, as I said, what we wanted to do was the average rate of change. So we needed the points in order to do that. So as we look at the change in X and change in Y between f of 5 and f of 2, right? So a great way to write that is, hey, the change in Y, the change in X, right? We use the little triangle here. It'd be delta Y, delta X. We're just saying the change in value. So we subtracted, or we're going to do the subtraction here. Sorry, y'all. We'll say, hey, let's go ahead and do negative 12 minus the 3 all over 5 minus the 2. Okay. Gives us what? Negative 15 all over 3 or negative 5.
Where is the 5 minus 2?
That's our X values. So remember, this is an ordered pair where we had our Y values that are spit out, right? Well, these are X values that we're choosing to plug in. Okay. Now, keep in mind, as you see here, I put the 12 and 5 right on top of each other. That's the important part here as well. Okay. Don't mix them up. No, as long as I said, like I said, as long as you see 12 and 5 on top of each other, then it's in the right order. Okay. Now, the one that you had to use, keep in mind, as I said, for each of them, I'm focusing on f of 2. Okay, that is one thing. Make sure that on each of your average rate of changes, that's the one thing that has to be consistent. Okay. Now, should we be surprised it's negative? Not necessarily, right? If you look at our graph again, going back and pick it on negative x squared, right? This is going to be a parabola going downwards. Okay. Now, what you could do is go find the vertex if you wanted to. We're going to look at the graph in a second. And that'll better help understand that, yeah, we should expect negative values. Okay. If you remember, you could do it quickly, just kind of a quick check. H equals negative B over 2A. Well, our B value is positive 2, right? Our A is negative 1. Well, hey, 2 over 2 times negative 1 gives us negative 1. Well, the opposite of that is positive 1, right? Now, that's an X value when you look at your H value. So since we're looking at the right side of 1, we're focused on this portion of our graph. So we should expect negative values, okay? Now, we'll talk about that a little bit more when we get to the graph and such, okay? Once we start talking about derivatives too, you're going to find that, hey, we have a great way to use vertexes in one way, but we also going to have another way to deal with it now too. Okay, that's what we're going to work towards today. But our focus here is just, are we good with getting to the negative 5? Okay, so if we look at that, and let me shrink this one down. We can do the same thing with the 4 negative 5 here. So we'll have negative 5 minus 3 all over 4 minus 2. So this one gives what, negative 8 over 2? Negative 4 now. Okay, still going down, but remember, negative 5 is steeper than negative 4. So the average rate of change is negative, but not as much as it previously was. Okay, we go with negative 4 there. All right. Are we good then with negative 3 when we look at f of 3 and f of 2? Okay. Hopefully you're seeing here, like I said, just kind of doing a quick reminder of the vertex here. When we need it, we'll go over more details. Okay, I'll make sure to do more, just doing a quick reference. We're on the decreasing side of our parabola, so we should expect all of those to be negative. Okay. Any concerns with those though? Now, the last one here, let me make sure that we had was I wanted you to do f of 2 and f of 2, but the problem here is if we try to do that, we get 3 minus 3 all over 2 minus 2, right? That gives us 0 over 0, okay? And remember, from math perspective, that's an indeterminate form. There's nothing we can do with that. Thank you. Nothing we do with that. However, we have a way around this, okay? The way around this was using the difference quotient with the limit. Okay, so that's what we're going to review real quick, and we're going to then look at each of these with that graph I have here. Oh, excuse me. So I'm going to rewrite it real quick to follow kind of what we just did. Okay, so in general, what we looked at is, hey, f of 2 was our focus, right? And we picked different h values. That would be our delta y, right? We shrank that down, though, to that last one was 0, which doesn't work because that gives me 0 over 0. So make sure you keep that in mind. When we put h as 0, it ran into issues. But this is where the difference quotient helps us out. So this one is, I'm using 2 instead of x in general, though. Keep that in mind. Our focus was 2. But with that limit in place, now we have a way to work through this. H can be 0 because I'm going to be able to deal with it. But remember, it's just a simplification game here, okay? So f of 2 plus h is one thing we have to go get. And I said 2 and 3, right? All right. Now, understand, we practiced this yesterday. The whole point of this, though, is to kind of show that progress as we just looked at, right? And that's why I have the graph over here for us on the side. But if we go through and simplify this one, all right, we use something that looks like this. Now, what do we need to be careful with this one since we use 2 instead of x? Does anybody see something here that's can simplify? Right. We actually can simplify this one, right? Because remember yesterday when we had x plus h, I wasn't able to do much, right? But here we have to be careful. Since I chose 2 plus h, we actually have a couple things we can't work with. So that would go down to negative 2h. But also make sure to see here, the 4s are gone. Okay, that goes to 0. Now, I did several steps there at one time, so make sure go back and look at the one we did yesterday. Okay, I squared it and then distributed the negative. Now, with that in place, that gives us negative h squared minus 2h plus 3. And remember, f of 2 was positive 3, right? That's another thing that we want to make sure to remember. So now we can go in and do this limit. Just remember, though, f of 2 was just 3. That's where this one's coming from now. Okay, we did plug that in. We like that, though, because what's right in front of the minus 3? Plus 3, right? That works out kind of nice. We like it even more now because what do the only 2 terms have on them that's left in the top? They both have an h, right? And I can then do the division of the h in the denominator, right? Just remember, as I showed the other day, you have to divide this h into both of those terms, not just the first one, okay? So make sure you do into both terms. So that would give us the limit as h approaches 0 of negative h minus 2. Okay. Now, it's definitely a little bit more work, and I'd understand you might have a few more steps. But like I said, as far as those full steps worked out, make sure you look at stuff we did on Monday. Sorry, not yesterday. Okay. With that said, we like this situation because I can now just do a direct substitution. I don't have to worry about that h in the denominator, right? I could plug in 0 here, that's gone, and I'm left with negative 2, right? What I just was able to find was what's the average rate of change, actually what we're going to call the instantaneous rate of change at negative 2. Okay, well, what does that look like on the graph? Well, first and foremost, remember our main point here was x equal to 2. All right, if we kind of zoom in a little bit, you'll see that it kind of looks like it goes right through 3. I know I had to shrink my y-axis a little bit, okay? But that's going to be the 0.23 that we found to start with, okay? The other points that we looked at were 5, 4, and 3. Now, what you're going to find here is that when we talk about rates of change, I kind of pointed out that we kind of dealt with this with lines already, right? The rate of change of a line is constant. So when I did this difference quotient situation with a line, we got the slope back, right? Well, that gives us something that we can then compare. I can draw some lines through each of these points here. And what we'll have is what we call secant lines. Okay. Now, the secant lines here do change a little bit as I go, based on the slope and the points we're using. Okay. So as we saw here, this slope was steeper, right? But the reason we call it a secant line is because when I draw the line, it touches my graph at those 2 points that we picked. Okay, so understand if we say something about a secant line, we're going to have to use the word average rate of change because it's just looking at the behavior over a period of time, right? We're just saying, hey, as I go from 2 to 5, what happens? We don't necessarily ignore everything in between, but we don't accurately represent everything in between either. Is that clear to everyone? Now, what we like to do with mathematics, though, is say, what happens if I start trying to get closer to a particular point? Well, what we saw is here is we still had a negative rate of change, but the number was a little bit smaller. And again, as we saw with this, it kept shrinking down, okay? Now, if I take away these lines here that I called secant lines, and we focus again at that point f of 2 of 3, equal to 3, sorry. What is special about this line that we're looking at when I just use that point alone? It intersects at f of 2. Does everyone see that? How many times does it intersect that graph now, though? That's the question that we want to make sure we ask. Just one. It just touches the graph at that one point now. So it's no longer a secant line, right? And this is an important step where we could say, hey, I no longer have an average rate of change. I now have an instantaneous rate of change. All right. And I kind of introduced that yesterday, right? This instantaneous. I know what's going on at that particular point. What we see here, another great way to write this would be like, hey, I just found the slope of the tangent line. So we could be like slope of the tangent line. You might write something like m with a tan underneath there, but I'm just simply shorthanding that, hey, this is the slope of a tangent line now. And as we move forward, that's really what we want to focus on, the instantaneous rate of change and this slope of a tangent line. Now here again, I just picked points, right? So that's why I'm saying this is a particular line we're looking at. But if you remember yesterday, we wanted to use x plus h, right? Kind of generalized. How can we use this for all points, not just a particular point? Now, what we see here, if I could pull it up, let's see if it works. I was afraid of this, y'all. Oh well. I should have kept it open. That's all. I had something that visualized that. But as you saw, I drew the different secant lines, right? As we move the secant line, we're changing that slope. It approaches the tangent line. What allows us to get to the tangent line, though, was that limit notation, okay? Now, remember, as I said, limits are important for a course, but it's not something we have to do all the time, okay? So keep that in mind. So let's look at another one. Now, I'm saying identify the equation of a tangent line here. Now, the main thing we want to find that we're looking at is we definitely need to know the instantaneous rate of change at x equal to -3. I just want to make sure to show you here what's another way to apply what we just used, okay? The first step we have to go look at, what's that instantaneous rate of change, okay? Our focus, though, is that -3. So let's first go find what f of -3 is. We're on agreement with -1/5. All right. Now, with that said, let's go through the process that we just did, where we say, hey, f of -3 plus h minus f of -3 all over h, okay? Now, the reason we're doing this is going to give us that instantaneous rate of change. The slope of the tangent line is another way to write that, but make sure you remember instantaneous rate of change. Okay. Now, with that said, this one's not as bad to plug in the -3 plus h. Just make sure you see here, this is going to give us h minus 5 plus 1/5 all over h. Okay. The difference here is when you plug this in -3 plus h, you'll be able to combine these just like we did before, but the h stays there, right? Make sure you see here, since this is -1/5, that's why I changed that to plus. Okay. Now, this is another one that I just want to make sure to show you if it comes up. Whenever you have rationals whenever you have fractions, within a fraction, you want to eliminate the extra fractions. Okay. The way that we handle that is multiplying by the common denominator on top and bottom of our fraction. Okay. The reason we like this is I can then distribute this to those two fractions. Just make sure you see there with this first fraction, the h minus 5s will drop out. Okay. These fractions, I plugged in -3 into here, but keep in mind, it's positive right now because we were subtracting, okay? And then, as I said, we plug this into here as well. So that's why I was saying if you plug that in, -3 plus h minus 2, all you're going to be able to do there is combine those values, okay? Now, keep in mind, like I said, I'm doing this for the sake of building to something right now, okay? The ones that you definitely want to be comfortable with simplifying are the ones that we did Monday. Make sure you have stars kind of like, hey, quadratics, linears, those to me, I feel are more fair as far as like, just make sure we understand the process that, hey, simplify and that'll get us to what we need. Is that clear to everyone? This is another example. If you remember, on Monday, I did this example. I said, don't even worry about copying this down. Just know that this is, if it came up, this is all that we have to go through, right? This is another special case. Like, what if you have fractions involved? Okay. But make sure you see here as you distribute this to these two terms, what you're doing is saying, hey, oops, let's get rid of the denominator. So this first one, the h minus 5s go away. So I'll have just 5, but the second one, I'll have h minus 5 left over. Now, what's nice about the numerator, once I am able to get rid of the fractions, right, the fives are gone, right? What's even nicer, though, is what you're going to find here. Once those are gone, what else can we divide out? The h's, right? And once those h's are gone, this is where it gets really helpful. Because with those h's gone, I can plug in 0 directly now, right? I can evaluate the limit through direct substitution, because what is 0 minus 5? -5, right? And remember, we have that other 5 here, so that'll give us 5 times -5, or -25. Just keep in mind that's in the denominator, so it'd be 1 over that, okay? Now, what we're seeing here is that is going to be my instantaneous rate of change, or the slope of the tangent line, okay? What is my function doing at that point? How would you interpret that as far as describing the function? Is it increasing, decreasing, or constant? It's decreasing, right? Well, let's go confirm that, right? What point did I say to use? Oh, crud, y'all. I totally graphed the wrong point. Is that what I had here? Sweet. All right, there we go. We'll look at -3. Make sure you see here on this graph, it's slightly going down, right? Hence why it's -1 over 25. It's not a huge decrease, but it's definitely decreasing. Okay. Now, as you saw there, I copied the wrong side, my bad. But using this graph, we can see that we have that drop down. So if I wanted to add something here, the tangent line, right? The next step of that would be to find the line itself. Okay. Are we good though with how the -1 over 25 is the instantaneous rate of change there? Okay. Then the next step, then, since I want the equation of the tangent line, remember, all you need to do at that point, let's get this out of the way because that's wrong. What we need to take for that next part is the point that we're working with. And that slope that we found. Okay. So we did all that work to get to the slope. We already had the point. That was the nice thing. But if you remember, to find the equation of a tangent line, right, we can use the point slope form of a line. I know this isn't the only way to do it, but I think you'll find that with this fraction involved, this will probably make it a little bit nicer to work with. Okay. Just make sure we plug in the values that we have. Because we're subtracting and they're both negative. Kind of like what we saw over here with this one. Because of the subtraction, right? When I plug a negative in there, it becomes addition. So we have to be careful of that. And what you're going to find here, this is actually comes from the average rate of change, right? The slope formula is the average rate of change. Same thing when it comes to lines, okay? Now, the part that, as you see here, is gonna be fun. I gotta distribute, okay? Make sure you see there, though, that 3 goes in the numerator. And then we have to find a common denominator, so that'll give us, what, 5 over 25? Mm-mm. So it'd be negative 8 over 25. Okay, and that would be the equation of the tangent line. So this is the tangent line here. So negative 1 over 25, negative 8 over 25. Let's go confirm that our work is what it's supposed to be, right? Okay, that's why I still had this one up and not the other graph I wanted to show. Okay, so if we graph that, we would say, hey, y equals, we said negative 1 over 25, right? And we got, nope, minus, and we said 8 over 25, right? Now, as you can see here, the line kind of cuts through all of that. But as we zoom in on negative 3, what we want to see is that it's not touching. I was about to say. Technology is not always my best friend. But as I go in here, how many lines do you see? Right. The closer we get, the more indistinguishable it is from the line itself. And this is why it's so helpful, right? As you can see here, as I go in there, we can start kind of seeing the comparison from the graph and the behavior we see there. Now, as I zoom back out, we start to see that separation take place, right? So it's good for, situations that are kind of close to it, right? But for that moment, it's a great representation of what's going on, okay, around that point, right? Remember, our focus was that negative 3. If I go out here and kind of look at, negative 24, well, hey, that doesn't help me at all. Everyone kind of follow that? Now, I did mean to do a positive number because we're going to find a lot of times we're going to be focused on positive numbers because we're going to be dealing with time maybe, right? So keep that in mind. But in this case, hopefully you see just coming from a visual approach that, hey, secant lines is what we get from the average rate of change. But when we bring that limit in, I'm working towards a tangent line, okay? Any questions with that I could help clear for someone? All right. Well, things that we have to put in place then before we jump forward, because now that we have that in place, we can start talking more about this differentiation. What is a derivative and how do we use it? Well, the good news is we've already done it. Okay. Whenever we look at it, by definition, a derivative of a function comes from the limit as h approaches 0 of the difference quotient. So if we want to differentiate a function, this is the limit definition. Now, keep in mind, as I've mentioned before, this is just a definition. We're not necessarily doing it all the time. Applying it is what we want to focus on. And we're going to see a couple problems here where we start catching patterns. We don't have to go through that whole limit process every single time. That would get tedious if we had to do that every single time. Okay. Now, with that said, though, I have a random function up here that I want to graph. Okay, and as you see my directions say, hey, where is the function not differentiable? Well, a couple things that we have to watch for. First and foremost, has to be continuous. Okay, so does anybody see a point that you would say is not continuous on this graph? What point would someone say stands out to? All right. I heard 8 definitely, right? What's wrong with 8 when we talk about continuous? It's a hole in the graph, right? So it has a limit, right? Make sure you see here that as we look at the limit of this, from left to right, the limit would give me something. But the problem is when I go to do f of x of 8, it does not exist, right? There is no value. Okay, now keep in mind, it could be a rational function that we restricted it for, right? Who knows? All right. And I thought, did someone say 7? Why is 7? right? It's a whole, this would be kind of like a jump discontinuity in a sense, right? Or a removable discontinuity would probably be the more proper way. What you're seeing again here, the limit, oops, the limit exists, right? So everyone see how we go left to right, the limit points that value. But what we see here is the limit equals a, right? So if I look at the limit of the function as x approaches x7, it equals a, but f of x7 equals b. They're different, they're not the same. So that would definitely be discontinuity. Asymptotes is another one to watch for, right? So remember, as we just looked at this graph, I think I actually had a graph, didn't I? I put that dotted line there on purpose, right? The dotted line I have there is the vertical asymptote of this graph. That would be another example of discontinuity. Is that clear to everyone? Now, with that said, then, the main thing that we want to add to this then is watch for sharp turns. Okay? Any sharp turn will not be differentiable. So things to kind of highlight here would be these points as well. All right, the reason we run into issues. If I try to draw a tangent line on this top one here, doesn't that line only touch one time? What about this line? Don't they both satisfy? But really, I could have picked any slope in between both of those, right? One negative, one positive. Which one do we use? I could pick, in fact, if we want to, we can do a constant slope there. And that's where you run into, anytime you have a sharp point, there's going to be some issue as far as focusing on a specific point. Whereas we just saw with our work here, how many slopes did we get when we did all that? And we see we got one clearly defined slope, right? So what you're going to see here is things to watch for, okay? What's one function that gives us a sharp point that someone remembers that kind of looks more like this? Absolute value, right? If y'all remember, the graph of absolute value gives us that V shape. So it would look like this. It's continuous, right? The limit and the function value are going to be the same, but it's not differentiable at that point. Make sure you see it's at that point, though. That's why I like this little graph I found. That it's at that particular point is where it's not differentiable. Make sure you see here, we had several places where, hey, we're good here, we're good here, here. All those other intervals, I'm differentiable, right? They're continuous and differentiable. But the whole function itself has several places that we have to make sure that we're aware of, okay? Is that clear to everyone? Now, sometimes we're going to find ways that you can change it to make it work, okay? But that'll all be kind of situations that, hey, we got to watch for them and make sure we handle it when it comes up. Everyone go with that? Well, let's go put that to practice then, okay? So what we have here are two different functions, right? I probably only have time to do one. So let's just focus on the linear one since we kind of know what to expect here. We'll do this one later. Let's just copy that out the way. Let's do that. I'm having too much fun, y'all. Hopefully y'all are too. Okay, now hopefully you see here, I have that limit definition of a derivative, okay? This is our instantaneous rate of change, but I'm now gonna call this differentiating. This is the derivative function when I'm done. What that means is the resulting function I get, whatever x value I plug in, it will give me the average rate of change at that value. Is that clear to everyone? Now that's for the derivative notation. As you see there, I put f and what we're gonna call f prime of x. It's in a superscript. If you remember other situations where we use that would be something like this. What does that one represent? Anybody remember this notation here? All right, that would be an inverse function, right? So make sure we're always paying attention to what we're working with. This is an inverse function. Okay, specifically it's connected to f, right? We're not dealing with it, but just kind of keep an eye on your notation is the key. Okay, what you're seeing here, though, is the one thing that I want us to be comfortable with is that we're transitioning from just a change in x and change in y to the derivative of what we're working with. This is a big change. It's still changing x and changing y, but we're starting to make this change so small that, as you saw with that graphic, like it's indistinguishable as I zoom in on that. Okay, so it's no longer an average rate of change, but an instantaneous rate of change. Now, what you're going to find is nice about this moving forward, we're not going to have to do all this work over and over again. Okay. So with that said, remember here, this one if I use the limit definition, would give us 2x plus 2h minus 3. If I plug in x plus h, all I can do is distribute it, minus 2x plus 3, all over, I put x up here twice, y'all, I'm sorry. That should be plus 2x plus 2h. Now, make sure you keep in mind, I changed both my signs at the end because I distributed the subtraction to both terms, okay? Now, what we like to see here, though, is terms canceling out to 0. All right, all that goes to 0. Now, make sure you remember, though, we kind of talked about this one, so we shouldn't be surprised by what we find here. Because 2h over h will give me just 2, which equals 2, right? If I don't have anything to plug in h for, just say constant value, right? Remember, limit of a constant is so. What that gives us is that the derivative function of this linear function that I started with is just 2. Should I be surprised with getting the constant value 2 here? No, right? Remember, as I talked about, lines have a constant rate of change, right? No matter what point I pick, it's going to have a constant rate of change. We didn't have to talk about secant lines or tangent lines when it's a line itself, right? It's always going to be the same. That means no matter what point I pick, I can go up here and say at f of 3, yeah, it gives me what, 3 if I plug it in? Its average rate of change, though, is 2. Now, make sure, again, always be careful with your notation. F of 3 is 2 because that's me saying I'm plugging into the original function here. F prime of 3 is saying, hey, this is the derivative of this function, and it's always going to equal 2. Now, did the 2 get made up from somewhere random, or was it a part of this problem already? It was part of it. It was the coefficient of x, right? Hopefully what you see here is that constant term was gone, right? It was only that coefficient that was left over, right? So if I try one more as we finish up, if I gave you g of x equals negative 5x plus 7, what is the derivative of this? So if we just kind of take a guess, right? F of x was 2x minus 3, its derivative was what? 2. So if we have g of x equal to negative 5x plus 7, our derivative would be what? Not 5, but yeah, make sure you remember. That's a big deal, right? Because remember, that means my slope is negative, right? Now, that's nice about lines. And what you're going to find here is I was going to add to it with that other one. And we'll do that on Friday. We'll start building up these rules because what we're going to be able to do is have derivative rules. So we don't have to do that limit every single time. Okay. Now, what I will do is I might do a couple different quotients just to show you where it comes from. So that's why I want to do the quadratic. Once I do the quadratic, though, we'll have it for any polynomial. Okay. We just got to pay attention to the patterns that are taking place. Okay. Linears, hopefully you'll see here kind of nice. Constant terms or functions, that we'll see that as well. Okay. Any questions or concerns that I can clear up as far as jumping into this idea of a derivative function and how it represents instantaneous rate of change? All right. Well, that's what I wanted to focus on today. Make sure, again, though, you're always going back and reminding yourselves when you see stuff like this. It's like, hey, I might not do the limit all the time, but it serves a purpose, right? Make sure you keep that in mind. Okay. Have a good day, though, and as of now, I will not be here Friday. I'll try to call the doctor's office. I almost forgot. Sorry. I'll try to call tomorrow to see if I can get my appointment changed earlier. But my plans for Friday is we're going to do a Zoom. No, we don't need to come in person. We'll do a Zoom. It may only be like 30 minutes, okay? Y'all, so keep that in mind, but we'll do a Zoom on Friday. Everyone go with that? All right. We'll see y'all on Friday through Zoom. Mm-hmm.